Dear colleagues, please let me allow to introduce you and analyze the physical and structural properties of oak wood from historical constructions made by a team of researchers of the Department of Wood Science and Technology of the Biotechnical Faculty of University of Ljubljana. The aim of our study was to analyze the aging of wood. It might be present during its service life when the wood is exposed also to photodegradation, biodegradation, surface and internal structural changes. The process is mostly interpreted as a slow, mild thermal oxidation in the area of natural temperature fluctuations. The wood originated from the collection of samples of the Department of Wood Science and Technology. It was obtained from recently felled trees and from historical constructions in Slovenia, from Castle Pišece, Stična Monastery and Ban's Homestead. The sections of constructions were taken during the renovations in 2004, 1999 and 2005. After collection in the field, they were used to study their building history. Afterwards, they were stored in the containers at room temperature and protected from the light. Wood discs were sanded and high-resolution scanned. Afterwards, we continue with the growth ring width determination and dating using CoRecorder and ZAP program. Afterwards, we made the characterization of anatomy and structure, color, wood density, hardness, shear strength, hygroscopicity, and dimensional stability. From the data, we built 5 age groups. The age group 100 contained wood from the recently felled trees, while the samples from the age groups of 300 to 600 originated from historical structures. As is seen from the image on the left, polarized light microscopy of aged oak wood did not detect any cellulose degradation. Even epifluorescence microscopy of aged oak wood did not detect any changes in lignin. We found out greater lignification of libriform fibers. However, some chemical changes of aged oak wood were found by FTIR spectroscopy. We confirmed the decrease of hemicellulose ratio with aging of oak wood. In contrast, the lignin content did not show changes with wood aging. Both the visual and LAB determined color parameters of oak wood showed that the wood became increasingly darker with the increased duration of service life. The results also showed that the aged oak is less hygroscopic than the recent wood. The absorption coefficients of aged wood, groups 300 to 600, were on average significantly lower. The same was found also in absorption isotherms. We confirmed also small improvement of dimensional stability of aged oak in tangential direction and therefore reduced shrinkage anisotropy. The density of aged oak wood was not reduced significantly and varied with growth ring width and proportion of plate wood. The wood density also significantly influenced hardness of wood in radial and tangential direction. Slight decrease of shear strength, however not significant, was determined also at aged oak wood. The shear strength of wood was positively correlated also with wood density. As the results show, aging has caused small structural and physical changes to oak wood. Besides aging, we presume that also the location of wood during its service life and exposure to climate fluctuations seemed to influence the physical and structural properties of historical